Good afternoon, everyone. I'm Joyce Leung from San Jose State University and Enhancement. Last summer, I did my NERTO with Mr. Jeff McQueen and his team from NSAP EMC, working on evaluating the GFS every planetary boundary layer heights, PBLH, and related fields in recent wildfires. Starting mid-August 2020, there were multiple wildfires in near the San Francisco Bay Area, including the SCU Lightning Complex, CCU, and LMU Lightning Complex. And the resulting smoke has spread not only across the state, but across the country. And air quality in California has fallen to dangerously poor levels. And the satellite image on the left shows the large plume of wildfire smoke, and the middle picture shows downtown San Jose being obscured by smoke. So with wildfires becoming more frequent and severe, there is a growing need to simulate and predict the impact of wildfires on air quality and human health using numerical models like CMAQ, Community Multi-Scale Air Quality Model. And in July 2021, GFS Every3 replaced NAM to be the driving meteorology of the operational CMAQ. So in this study, we evaluated fields important to air quality, including PBLH, temperature, and dew point, to see if there are any improvements and try to understand localized model behaviors. So we want to look at PBLH because we've got some new ceilometer measurements in the Bay Area. And apart from meteorological fields, we also look at PM25 predictions by CMAQ because that's one of the major outputs of CMAQ and also is one of the major components of wildfire smoke. So we use backscatter intensity profiles and PBLH measurements from ceilometers and also observational data from weather and air monitoring stations. So the two stations that we have are Sacramento SACR, which is an inland site, and also San Jose State University, SJSU, which is nearer to the bay, and the extent of marine influence depends on the strength of onshore flow, and in summer, the typical pattern is onshore flow, so we expect marine influence would lead to low PBLH at San Jose. So the time series and maps of model outputs were visualized, and correlation analysis and verification metrics were used to evaluate the models. So here on screen shows the PBLH time series at SJSU. The black line is observation, blue line is NAM CMAQ, and red line is GFS CMAQ. And we can see that PBLH at SJSU is generally quite low. And on the lower left, we see the mean bias plot of PBLH at SJSU with by forecasted time. And the lower right corner here shows the scatter plot of observed versus model PBLH. So we see that GFS is over-predicting daytime PBLH and slightly under-predicting nighttime PBLH, probably due to near-surface meteorology or increased mixing due to excessively dry soil moisture in the model. And for the correlation coefficients, they are quite low for PBLH at SJSU with the value being 0.368 for GFS CMAQ and 0.350 for NAM CMAQ. Okay. So this is a backscatter intensity profile from the ceilometer at SJSU from August 18th to 21st. We can see some high-level smoke there, which was probably transported from a distant fire. And we can also see some near-surface smoke covering SJSU starting August 19th when the nearby SCU Lightning Complex started. This also shows how ceilometer backscatter intensity profiles can be useful in visualizing the evolution of the boundary layer and the vertical distribution of atmospheric aerosols. Okay, next, let's look at the time series of PBLH at Sacramento, which is an inland site. So we see larger diurnal variations and higher PBLH at Sacramento. And the models are able to predict the peaks of the PBLH here better at Sacramento than San Jose, although over predictions during daytime is still very common. And for the correlation coefficients, they are much higher here with values at around 0.6. Okay, so this animation shows the evolution of PBLH in the model run on August 17th at 12C. The left one is NAM and the right one is GFS. Okay, so we see that the pattern is similar to diurnal temperature change, and that GFS is giving higher values in at the corner. And another point to note is that the blue color representing low PBLH in GFS matches better with the shape of the bay, whereas for them, the blue color just goes all the way inland, which might show that the marine layer intrusion is too strong in them. So the models are doing a lot better in predicting 2-meter temperature than predicting PBLH. These plots are the mean bias plots of 2-meter temperature prediction at the two sites. The top row is SGSU and the bottom row is Sacramento. The left figures are errors before the fires, and the right figures are errors during the fires in August 2020. So at SGSU, we see that GFS is consistently predicting higher temperatures than NAM, and GFS has a warm bias, which this bias became more positive after the fire started, which might probably be due to the fire smoke blocking the sun and causing temperatures lower than model prediction. And at Sacramento, we see that the model behaviors are similar, with GFS having a smaller bias. And similar to the situation in SJSU, the error line shifted upwards after the fire started. And for dew point prediction, we see dry bias at both sites, and GFS is drier than NAM. And we see that the dry bias is stronger in San Jose than Sacramento, and the correlation coefficients are also lower at SJSU than Sacramento. Okay. Next, let's look at the CMAP PM2.5 prediction at SJSU. This one shows the hourly PM2.5 prediction and observation. And from the observation, we see that there are several peaks starting August 19th when the nearby SCU lightning complex started, and then the peak slowly died down. And at this site, at SGSU, GFS probably missed the fire emission source. So you can see the red line, it was constantly low throughout the month. And whereas NAM was able to capture the fire emission source, but the magnitude of PM2.5 was too high. And at Sacramento, the result is very different. Here from the observation, we see peaks with increasing magnitude starting August 18th, reaching a maximum on the 23rd, and then the peak slowly died down again. And this time, GFS was able to capture the fire nearby Sacramento, but the model overshoots on the 20th and 21st. And also, we can see that the emission source in GFS was not sustained, that after the two peaks, the PM level quickly returned to a very low level. And on the other hand, NAM was able to capture the fire and have a more realistic prediction of PM2.5 level. And to understand why the model behaves like this, we try to look at the PM2.5 AOD map. This is the GFS map PM2.5 AOD map at forecast time August 21st at 21 UTC when the GFS model overshoots for PM. We can see that the model was able to capture the LNU lightning complex, but the magnitude of PM2.5 was too high. Whereas at near SGSU, we see that GFS missed the SCU lightning complex, as shown by the absence of high AOD to the east of San Jose. So I think this might be improved by maybe assimilating data from ground-based observation or changing the physics schemes to determine lifting, mixing, and transport of smoke. And this study has some limitations because of the sample size and salinity properties. So for sample size, we only looked at data from 1 month, so the correlations might not be conclusive in telling us about the model performance, but we learned more about the model behaviors at an inland site and also another site nearer to the bay. And second, site selection is limited to the salinity locations. And last but not least, salinities are not that accurate during certain weather conditions, but the quality assured measurements would add value to model PBLH evaluation. So to summarize, we see better GFS CMAP performance at the inland Sacramento sites than San Jose. And it shows a warm and dry bias at both sites, which might be improved by changing the land surface model or using bias correction. And last but not least, GFS CMAP has some skills in capturing fire events, but occasionally it might miss some fire hotspots, and the magnitude of hourly PM2.5 can be improved, maybe by assimilating ground-based observations or changing physics schemes. So I would like to thank NOAA, NCAS, and my NOAA mentor and co-mentors, and also my advisor for this meaningful experience.
We have time for a couple of questions. Yes, Laura?
It's a really interesting study. You mentioned the importance of the land surface model. Do you have any observations, like of surface fluxes or anything, any way to get at that in terms of like sensible latent heat flux? And because you also mentioned the impact on the solar radiation, so I kind of think.
Sadly, we don't have any of those observations. We really want to look at that and compare model and observation of the surface heat flux, because we think that might be the major reason why GFS has that warm and dry bias, but we don't have data for that.
Thank you.
Thank you.
Just one quick note on the no data issue. There are a couple of Ameriflux sites nearby San Jose. Those sites are, I think, run by the faculty members of the University of California, Berkeley. And I forgot the other university, I think it's California State University. But they are very close to San Jose. They have about 3 or 4 flux tower sites where you can get the heat fluxes. Any other questions? Yes.
Do you mind going back to like maybe like your second slide? It was like in your introduction, kind of, where you talked about why you were doing this. Actually, there's one right now. Okay, just kidding. It was one before. Sorry.
One more.
The next one.
Maybe it was what you said when this one was up. It was one of these things. But okay. But great presentation, great.
Thank you.
We're sure to see you again.